splines, local weighted regression. So this section is actually about more classic non-parametric regression models. So in statistics, actually. And so they are kind of like extension from a linear regression. So take a look at this example. The real trail data. So suppose we want to fit a model between volume, the response variable, and one predictor variable, which is average temperature. If we fit a linear model, then we'll get a model like this. So this means although you see from the scatter plot between average temperature and volume, we can see somehow a nonlinear pattern, somehow like this, at least. But if we are forced to use a linear model, we can still do it. Then the model will look like this, okay? And of course, this plot is created using ggplot directly. And if we call the GM smooth function and method equals LM, it will automatically overlay a linear model for us. What if we get rid of this method equals LM? Then it will actually overlay a local weighted regression curve. So this one is actually the default option. Okay? I show it here because I want you to know it is a local weighted regression model. So this is actually a non-parametric regression model, which is very flexible. We will talk about it at the end of today's lecture. So this is just a comparison of different models on the same data set. So apparently this one is better compared to the linear model. It captures the pattern more precisely. So now we'll move beyond linearity. So linear models have advantages because they are easy to fit, easy to interpret and do inference. However, oftentimes they underfit the data because in practice, it's very rare that there is a linear relationship between two quantities. So now we'll relax the linearity assumption and examine extensions of linear models, such as polynomial models, polynomial regression, splines, and local regression. So all of the contents in this lecture is from this book, An Introduction to Statistical Learning. But this is a very good textbook for machine learning, theories in machine learning. So this slide contains an outline of the models that we will talk about today, except for the last one. The last one is another level of extension, so I won't talk about this. I will talk about all of these from polynomial regression. Polynomial regression just is the immediate extension of simple linear regression. So by adding polynomial terms like squares or cubic terms, etc. And regression splines divide the range of x into k distinct ranges. And then within each range, it will fit a polynomial regression model, regression spline. And then smoothing splines. So this one considers the bias variance trade-off by adding penalty terms into the loss function so that the curve will be smoother, not so weakly. And lastly is local regression. So this one is similar to splines, but differs in an important way. The regions are allowed to overlap. In spline, you see the regions are distinct, so they don't overlap. But in local regression, the regions actually overlap with each other. This is an outline. Let's start from the beginning. Polynomial regression. So this is just an immediate extension of simple linear regression by adding some polynomial terms. A simple linear regression will be just like this. Let's now just consider one predictor, only one variable. Then you can, if you think there is a nonlinear relationship between x and y, you can add a square term or even a cubic term or even higher degree terms. So in theory, for large enough d, d is the degree of the polynomial. For example, if the maximum order term is the cubic term, then d is 3. Right? So for large enough d, a polynomial regression allows us to produce an extremely nonlinear curve. So it can be, theoretically, it can be used to model any shape of relationship or pattern. Right? And notice that this model can be easily fitted or estimated using the least square method. We can just consider each term as an individual predictor and just use the multiple regression, the least square method to estimate these data. And so generally speaking, it's unusual to use very higher order terms, okay? Like more than 3 or 4. Because if d is too big, then the polynomial curve can be overly flexible, right? And the shape of the curve may be very strange. It may be very strange. Overly flexible is not recommended. So let's use one data set, which is the weight data set built in this package, ISLR. So this is a package associated with the textbook I just mentioned. Right? Introduction to Statistical Learning with R is ISLR. So, so let's study the relationship between age and wage. So this data set contains wage and other data for a group of 3,000 male workers in the Mid-Atlantic region. And in particular, we just consider two variables, wage and age of the workers. So if we create a scatter plot, you see it looks like this. It's very difficult to figure out the true relationship between wage and age. Is it linear or non-linear? Is the slope positive or negative? It's very difficult, right? Anyway, let's start with the polynomial regression. Okay. Let's just blindly choose a 4th degree polynomial regression. In R, we can still use the LM function. LM stands for linear models. So in general, a polynomial regression model is also a linear model. Okay, so we can use it to fit it. And specify the formula. You see, we use this formula, wage to the poly age 4. So this poly command allows us to avoid writing out a long formula with powers of age. So this just means we consider x squared, x cubed, x to the 4th, all of these 4 terms. However, this is not exactly what it does. Right? The function actually returns a matrix whose columns are a basis of orthogonal polynomials, which means each column is linear orthogonal combinations of the variables. So let me explain that clearly. So consider the degree of term. 1, 2, 3, 4, or we can call them poly 1, poly 2, poly 3, poly 4, right? Corresponding to these 4. Okay. Then poly 1 is just x itself. Okay. And poly 2 is a linear combination of x and x squared, okay? Or a weighted sum of x and x squared with some weights, such so that these 2 terms are orthogonal geometrically. Okay? Right? Yeah, we can use linear algebra tricks to make them orthogonal. And the third polynomial term will be a linear combination of x, x squared, and x cubed. And again, we construct this polynomial term in a way that this one is orthogonal to polynomial 2 and a polynomial 1. Okay. And the last one will be a linear combination of all of the 4 terms. Because we know that because all of these terms are based on x itself, naturally they are correlated. But this polynomial command or function will automatically create basis functions of these 4 terms so that these 4 polynomial bases will be orthogonal with each other. Yeah. And then if we fit the model using these 4 terms, including the intercept, we get this result. Okay. And the coefficient table shows you whether or not each term is significant. So apparently, until here, the p-value of the polynomial term is very significant. But this one is, the p-value is slightly greater than 0.05. So this one is not significant anymore. So at least the cubic term is still significant. Alternatively, we can also create the raw polynomial terms. We just need to specify this argument, raw equals true. Then each of these terms will be the individual polynomial terms. The first row will be x, and the second row will be x squared, and the x cubed, x to the 4th. And you see the p-values will be different from what we have observed before. So if you are really curious about the relationship between y and individual polynomial terms, you should do this and let raw be equal to true. All right. And then let's fit this 4th degree 4 polynomial and also add the prediction to the weight and plotted. So this add predictions function can be used to add the fitted y values to the original data set, and we call it weight 2. And then we can create this plot. So the blue curve is degree 4 polynomial model we created. And we can also calculate the 95% confidence interval for the mean response. In particular, we use this predict function to do prediction for our data, x variables age. And the model we use to do prediction is the fit. Fit is what we got from previous slide. And SE equals true means I will want to calculate the standard error of the mean response. And then I pull out the standard error. So that is SE. And then we can use these formulas to calculate the confidence band. Predicted value plus 2 standard error is the upper band, upper band, yeah. This curve, and then this one is done. All right, so from this plot, you can see that when there are a lot of observations in the very dense region, in the region with a lot of observations, the confidence interval is very narrow. However, in this area, when we have fewer observations, the confidence band is very wide, right? So keep this in mind. This is very common to observe. Okay? It is basically because if there are in very sparse regions, right, we have fewer observations, then the standard error will be big, very big. The standard error is in theory S over square root of n. So it has a negative relationship with number of observations. If there are only a few observations in a region, then the standard error will be big. Consequently, the confidence interval will be very wide. Right. All right, so this is our initial stating for polynomial regression. And then you may wonder how to choose the degree of the polynomial. There are so many choices. simple linear regression or second order, third order, right? So which one is the best? We can actually use a ANOVA test to do so. For example, we can fit 5 models, starting from the simple linear regression model with only 80 cells, and then add H squared and then H cubed until degree equals 5, moving x to the 5th. And how to compare them? We can use the ANOVA function in R to do analysis of variance F test. So this ANOVA function can be used to compare, for example, at least 2 models, M1 and M2. Okay. To test the null hypothesis that M1 is sufficient to explain the data against the alternative that you need a more complex model, M2. So from this description of the model, you know that we assume that this M1 is nested in M2. So if this is M1, then M2 has to include all of the terms in M1. It's a larger model, more complex model. And then the ANOVA test will see if M1 is sufficient and M2 is not necessary. Okay. And in general, it can actually compare multiple models at the same time, as long as they are nested. So in our example, we will consider 5 different models. Gradually adding terms, we make the model more and more complex. And then we can compare them at once. Just make sure that you put them in the right order, from the smallest to the largest. Then I see the result. Take a look at this part. So the first model is here. Residual sum of square is equal to this. And then the second model is fit 2. Fit 2. And then you see the p-value of the F test is very significant. So this is the F certificate, that is the p-value. So this means square term is necessary because by adding the square term, the model is, the square term explains a lot of variation, right? And the contribution is significant. And similarly, the cubic term, the p-value is also very small compared to the quadratic model. The F test is also very significant. However, the x to the 4th, the p-value is over 0.05. So probably this is not necessary. And consequently, the degree 5 is definitely not necessary. So from this hypothesis test result, we know that a cubic or a quadratic polynomial appear to be reasonable. And probably cubic, because this is very significant. So D, optimal D should be 3. All right. So this is a test for polynomial regression. And if we don't want to do a ANOVA test, we can also just examine the coefficient table for the last model, because the polynomial terms are actually orthogonal. So each of the t-tests are equivalent to each of the f-tests in the ANOVA test, because all of the terms are orthogonal. So each of these t-tests are based on, marginal contribution of the model. Anyway, it's hard to explain. But anyway, this is consistent with the result. You can check the p-value, for example. For degree is 5.37, the p-value, right? Now degree is 5, this is 0.37, right? Same thing. All right, let's quickly move on to the next part, next step, basis functions. So polynomial regression models are, in fact, special cases of a basis function approach. So basis functions are a family of functions or transformations that can be applied to a variable x. For any individual variable x, we can create, for example, k basis functions. There are some functions of x itself. And instead of fitting a model in x, we can fit a model in the basis of x. So for example, we can create a model like this with k basis functions. And the polynomial regression model is apparently a special case of this basis model because we can just let bjx be x to the j, right? Then if the degree is d, then there will be d polynomial terms, including the first one. And we can use the ordinary least square method to estimate these betas for each basis function. Now let's step one step further. Go one step further. Right? They talk about piecewise polynomial. Piecewise polynomial. So previously we fit a polynomial model, one model over the entire range of x. Suppose this is x, this is y. No. We fit one model over the region. Piecewise polynomial is will not do this. Right? It will actually separate the entire region into intervals. For example, into 3 intervals. Right? Then it will fit a polynomial regression model on each interval. For example, here, and here, and here. Okay. So from this, from my plot, you immediately see there is a problem, right? Because if you do it, fit an individual polynomial model in each region without any restrictions, then the regression model may not be continuous even. Right? But anyway, we should start from here without any restrictions. Start from here. And let's see how to calculate the number of parameters in the model. Right? And by the way, the points where the coefficients change are called knots, or the points that are used to define the intervals are called knots. For example, in my plot, there are 2 knots. K is equal to 2 knots. If there are k knots, then we need to fit k plus 1 models upon, right? If there are 2 thresholds, then there must be 3 models. There need 3 models. So k plus 1 models. Yeah. All right. So now let's move on. Regression splines. So apparently the previous model won't work well because the model is even not continuous. Right? And in order to make the fitted curve smooth, we will put 3 constraints in the model. Right? So first, the fitted curve must be continuous. So i.e. at each knot, the fitted values from the left and right should be the same. So this is the first requirement. And secondly, the first and second derivative of the piecewise polynomials are continuous at each knot. So this will make the curve very smooth at each knot. And each constraint that we impose on the piecewise cubic polynomial effectively frees up 1 degree of freedom by reducing the complexity of the result. So by the way, we're talking about a cubic polynomial regression, cubic. So the degree is 3. That's because from our previous example, D should be equal to 3. That is the best model. If D is 3, we need to put these 3 constraints. Right? And in each interval, for each model, each constraint will free 1 degree of freedom. 1 degree of freedom. So the piecewise polynomial regression with D equals 3, and the 3 smooth constraints with the 3 smooth constraints is called a cubic spline. So this is kind of like a definition. Okay. D is 3 and with 3 constraints at each knot. In general, a cubic spline with k knots use a total of k plus 4 degrees of freedom. So let's calculate the degrees of freedom of the model. Degrees of freedom basically is the number of free terms in a model. In a multiple regression model, it's a number of predictors, right? But in this kind of regression spline, it's more complex, but in general, it's a total number of free terms in the model. Right? Let's see why the total number of free terms, the total number of the degrees of freedom is k plus 4 for a cubic spline with k knots. Okay. Suppose there are k knots, then we need to fit k plus 1 models, right? K plus 1 models. And then let's see for each model in each small region, how many terms we need for a cubic polynomial regression. So y is equal to beta 0 plus beta 1x plus beta 2x squared plus beta 3x cubed, right? So apparently for degree 3 polynomial, we need 4 parameters, right? 4 parameters. So each one has 4 parameters. Okay. Now don't forget, we put 3 constraints at each knot, right? And each constraint will free up 1 degree of freedom, which means it will decrease degrees freedom by 1. And totally 3 constraints, so 3 degrees of freedom will be freed at each knot. So totally, we will actually free up 3 times k degrees of freedom, right? And then let's summarize the result. 4k plus 4 minus 3k. So we get k plus 4. So that's why for a cubic spline with k knots, use a total of k plus 4 degrees of freedom. So namely, we have this many parameters to estimate. All right, so keep this in mind. And then furthermore, okay, as we have observed for regions at the 2 tail areas, left tail or right tail, we have fewer observations. So in those 2 regions, probably a polynomial regression is not necessary. It will overfit the data. So one way to resolve that problem is to further put more constraints on the boundary areas. So the function is required to be linear at the boundary. If we put this constraint to the previous regression spline, then we will free up 2 more degrees of freedom. So for example, for the cubic spline, originally we have k plus 4 degrees of freedom, then minus 2, we have k plus 2. Right? So if we do so, the regression spline is called a natural spline. So in the middle area, we have polynomial terms, and at the end, in the boundary area, we have straight lines, which makes sense, right? So this is called natural spline. And then how to choose the number and locations of knots. So this is apparently a hyperparameter that we can adjust. So one option is to place small knots in places where we feel the function might change rapidly, and put fewer knots where it seems more stable. Okay, so you just eyeball the plot and see how many knots we need. Okay. And another option, a more common option, is to place knots in a uniform fashion. Okay. So namely, you just specify how many knots you want or how many degrees of freedom you want in your model. Okay. And also specify the degree, the highest degree of the polynomial. And then the algorithm, the function will automatically calculate the number of knots you need and put the knots in a uniform way. For example, if k is 3, right, 3 knots, right, then it will, for example, if we only consider one predicted variable x, right, it will calculate the first quartile, the median, and the third quartile of your x values, and then use these three as the 3 knots, okay, 3 knots to split the data, okay, which is very reasonable. So this is the uniform way, okay, of splitting the knots. And how many knots should be used? One way is to use cross-validation, or you can try out different numbers. Okay. And so for now, we're almost done with the regression spline part. Let's briefly compare the two models, polynomial regression and regression splines. So regression splines often give superior results to polynomial regression. That is because in order to catch all the patterns in your data set, one single polynomial regression must require a higher degree, higher D, because you have to adapt your curve to different patterns in the entire region. But if we use regression spline, we first split the data into smaller regions, and consequently, in each small region, there are only a limited number of observations, and also the pattern won't be very complicated. Consequently, we can use a lower degree polynomial in each region. Right? And also because of the constraints we put on the knots on the curve, so we actually won't use a lot of degrees of freedom, although it seems that we fit a lot of models. However, the overall degrees of freedom won't be bigger than a single polynomial model usually. Won't be much bigger. So regression splines are better than polynomial regressions. And furthermore, smoothing splines. Right? So before this slides, we were talking about natural splines. Okay. At each knot, we have 3 constraints, and then we have two constraints on the boundary, in the boundary areas. Okay, a lot of constraints already, right? Furthermore, if we don't just fit it, then the curve, the regression line will try to minimize residual sum of squares. This term is similar to a regular multiple regression model. We try to minimize residual sum of squares in the training data set with a model like this. Right? However, it might not be the ideal case. And you may overfit your data. An extreme case is a model that interpolates all of the observations. Right? Then again, the residual sum of square will be minimized, will be pushed to 0. Right? However, the model apparently will not generalize very well. Right? So in order to deal with this problem, we can add a penalty term to the residual sum of square. The penalty term is lambda times integral of the second derivative of the curve. So if we use this as a loss function, we try to minimize this loss function, then the model is called smoothing spline. Right? It will make the curve even more smooth. And let's see why we use this, why this term can be used to penalize complex models. So consider, let me draw one. Consider two cases. This one. So consider this point. The first derivative is the slope. That is the first derivative. Yes. Let's see. Let's say this point is x. Okay. First derivative. Now, how about the second derivative? The second derivative is the derivative of the first derivative. It measures the change of the first derivative, immediate change of the first derivative. So it measures the wiggliness of the curve at that point. Okay. So for example, if you slightly change, shift it a little bit, you see that the slope will change a little bit. Okay. But for this curve, the second derivative won't be very big because the curve is very smooth, very flat. Okay. But consider another curve, somehow like this. Okay. Then the second derivative will be very big. If you shift a little bit, the first derivative will change a lot. Okay. So overall, from the examples, you see that the second derivative corresponds to the amount by which the slope is changing, or more precisely, the speed that the slope is changing at a point. So it is a measure of how rough a curve is, or the wiggliness of a curve. And by taking the integral of it over the entire region of X, so this is the measure of the overall roughness of the curve. Okay. So this term is, we put a hyperparameter here. So this one will control the complexity of the model, make it smooth. Okay. As I said, if you don't control it, then interpolation will be the best option. However, if you calculate the second derivative of this curve, it will be very big. So the penalty term will be very big. Okay? And definitely it won't be the optimal model because it adds too much loss into the loss function. Okay. And lambda is a hyperparameter. If lambda is equal to 0, then this is not penalized. And the curve will be very bumpy. When lambda goes to infinity, then the penalty will be very big. The f will be perfectly smooth, which means you have to fit a linear regression model. No wiggliness is allowed if lambda is approaching of infinity. And so lambda is apparently a hyperparameter that controls the bias variance trade-off of the smoothing spline. All right, then let's see. Researchers have derived the optimal model for a smoothing spline. Right. So they have some special properties, the optimal model. Right. The function f that minimizes the asterisk, which is this function, minimize the overall loss function, has the following properties. It is a piecewise cubic polynomial with knots at unique values of x and continuous first and second derivatives at each knot. Okay, sounds familiar, right? It's actually a cubic spline, right? With knots at unique values of x. And it's linear in a region outside of the extreme knots, which means it's a natural spline. So overall, we can summarize it in one sentence. It is a natural spline, natural cubic spline with knots at distinct values of x. And this is the optimal model. Of course, those 2 points are not about lambda, right? You still need to tune lambda, but the format of the spline is it is fixed, sort of. It's fixed. It's a natural cubic spline. It's nothing like this. All right. Yeah, how to choose lambda? We can use cross-validation. Right? It turns out that the leave one out cross-validation can be computed very efficiently for smoothing splines. So instead of actually fitting the model n times, theoretically using leave one out cross-validation, there is a formula that can quickly calculate the result. All right, now let's finally take a look at some examples. Okay. First, regression spline, piecewise regression spline. Right. Let's use basis function, right? ES to fit the spline model. So this BS is used to create basis functions for the splines. So we only have one variable, and let's just choose some knots by ourselves. Right? We observe the data and we think, okay, we need a knot at 25 and then 40 and 60. And this region does not have a lot of observations, so probably 60 is good. Right? So 3 knots. Yeah. And then we do the prediction and calculate results. So the curve looks like this. Okay. And then let's calculate the degrees of freedoms as a practice. So we have, oh, by the way, by default, this BS function will fit a cubic spline. Right? The degree is 3 by default, 3. So now let's calculate the degrees of freedom if we fit this cubic spline with 3 knots. Right? And if you use the dimension function to apply on this, so this part will actually create the basis terms. Right? So the dimension is 3,000 times 6. So 3,000 is the number of rows. That's not surprising. And 6 is the degree of freedom. So let's calculate if it should be 6 or not. So K is equal to 3 knots, and D is equal to 3, right? And then if we calculate the total degrees of freedom for a regression spline, we have calculated it should be K plus D plus 1. Okay. And consequently, it should be 3 plus 3 plus 1, which is 7. Right? However, the result is 6. So that is because it will not include the intercept. By default, there should be an intercept term included, right? But it's only the intercept. So for our output, we need to get rid of 1 degree of freedom for each 6. Okay. And similarly, if we don't specify the position of the knots, instead, we just specify the degree of freedom for our spline and check the dimension. Of course, we have degree of freedom equals 6. Okay. And then we can figure out the knots by using this attribute function. Okay. Pull out the knots. Okay. And you see 3 knots were chosen by the BS function. And these 3 knots are the 25th, 50th, and 75th percentile of age. So namely, if you don't specify where to put the knots, you only care about how many knots you want by specifying the degree of freedom, the function, the BS function will automatically use the uniform way to put the knots by using the percentiles. You can also change the highest, the degree. By default, it's 3, as I said, but you can make it 2. Okay? Then with the same number of knots, the degree of freedom will be smaller. Right? D is smaller. Right? And if you still want to have 6 degrees of freedom, there will be more knots needed for you. Okay? Because K plus D is equal to the total degree of freedom. If degree is 2, and total degrees of freedom is 6, then K must be equal to 4. Right? So you have to have 4 knots. And I will put it in uniform. And then let's fit a natural spline. To fit a natural spline, we use the NS function. So this will further free up 2 degrees of freedoms in the boundary area. Okay. And then naturally we'll need fewer degrees of freedom. So this degree equals 4 is equivalent to this degree equals 6. Right? The model is essentially the same in the middle area. The only difference is the model in the boundary areas. Okay? It's a straight line in the boundary area. So you see, it's actually better. You see the continuable is narrower, right, compared to this one. Is narrower, which is a good sign. So compare these two, you see natural spline is better. And lastly, smooth spline, right, with the penalty term. So R has this function called smooth spline. And you just need to specify the X variable or Y variable and the degree of freedom you want for the spline. Right? So it's quite flexible. So I chose a very big number for the illustration purpose to show you how wiggly it can be. So you see this orange curve is corresponding to degree equals 16. It's very wiggly. And at the same time, you can use cross-validation to choose the best degrees of freedom. So it will use leave one out cross-validation to quickly calculate the optimal degree of freedom for your data for a spline, smooth spline. And turns out that you see you can pull out the degree of freedom. This is the optimal one. Is 6.79496. It's not an integer. It is a number. It is a real number. And then because if we plot them together, you see they are not so different. Then by the principle of parsimony, we will choose the simpler model. Degrees of freedom equals this to be better. Okay. This is a smooth spline. And we have the last model. Okay, I will finish this part. Okay. So if you have to leave at 3:15, you can leave. Otherwise, you can stay. I will finish this part. The last model is local weighted regression, or the loess model, I usually will call. So the local regression is similar but different from the models, other models we have talked about, the splines. So this is a different approach for fitting flexible nonlinear functions. So it involves computing the fit at the target point using only the nearby training observations, local observations. Okay. Of course, you need to define the size of the neighborhood for any point. Right? That is defined by a parameter called spline. Called span. So let's see this. This is a simulated data set. Okay. the blue curve is corresponding to the true relationship, true function between x and y. Okay, and the orange curve is the fitted local weighted regression line. And then focus on this point. Then all of these orange points are the neighborhood observations or nearby training observations. And the model will fit a regression model using only these observations. So that's why it's called local regression. And it is local weighted. So this bell curve, this golden bell shape, shows you the weights of observations, right, using the model. The farther away the observations from the target point, the smaller the weights. The weight is kind of like follows a normal distribution somehow, right? But not exactly normal. But this one just shows you that observations that are closer to the target point has higher weight on the model for bigger influence on the prediction model. And for observation farther away has smaller weight. So that's why it's called local weighted. And then how about other observations? For example, the point next to it. Okay. So this is kind of the span, or you can consider it as a window. Okay. And then if you, for example, want to, you will shift to the next observation. So the window will be slightly shift to the next, for the next target variable, target observation. So that's why at the beginning we say that there is a big difference between local weighted regression and regression spline, because the regions overlap with each other a lot. Right? We'll fit a lot of models. Basically, we will fit one model for each observation in the training set. And then eventually do prediction for each one and connect them together to get a smooth curve. So this is called a local weighted regression. So for example, for this point, it will use all of these to fit a model and do prediction. All right. So how to define the weighting function? And so these are, we cannot talk about them. Just let's take a look at the span. The hyperparameter span is used to define how big the window is, the neighborhood is. The smaller the value of S, the more local and wiggly will be our fit, which is very intuitive. The smaller the window, I will use fewer observations, and the models will change faster. So consequently, the curve will be more wiggly. And S usually is defined as K divided by N. K is the number of observations in the neighborhood, and N is the total number of observations in the training set. Okay. So for example, so instead of actually fit a local weighted regression, we just first take a look at using the ggplot function to show the two cases. The first one, for the first one, span is equal to 0.1. So it will use 10% of training observations to fit the model for each observation. And the second one, span is equal to 0.5. So it will use 50% of observations to fit the model for each observation. So you see a big difference. If span is 0.1, the curve is very, very wiggly. But for span equals 0.5, it's much smoother. And this one also shows you, this one actually, we actually fitted the model. We can use the loess function to fit a local weighted regression model. Specify the formula, the span, and data set. Save it in Fit 7. And then the next one is a smoother model, Fit 8. So these two curves were created by putting the fitted result on it. And however, you can also use the GM smooth function in ggplot2 to overlay these local weighted regression lines by specifying the same span and span value. So see the results are exactly the same, which means ggplot2 also uses this loess function to overlay the smooth curve. By default, it uses that. But for very large data set, GM Smooth actually will use GAN function, generalized additive model, right? So this is faster for bigger data sets. All right, perfect. We are only 5 minutes late.